Welcome to our fourth AI4Copernicus Café. Today we have the pleasure of having with us Dr. Vincent-Henri Peuch, and we will be discussing about the fourth industrial domain of the first round of the open calls, that is the health sector. Dr. Peuch is the director of the Copernicus Atmosphere Monitoring Service and the deputy director of the Copernicus Department at the European Centre for Medium-Range Weather Forecasts. He is an internationally respected scientist working on numerical modeling and data assimilation of air quality and atmospheric composition. It's a great pleasure to have you with us today, and we look forward to your presentation.
Hello, thanks, Xenia. Hello, everyone. So thank you very much for giving me the opportunity to present a little bit on health, and particularly on the impact of air quality and health. Okay, this is my title. So the first thing is, before going into detail about why air quality matters for health, I've always been looking for figures to try capture that in a single slide, and the one I've found is actually I find it quite revealing. So maybe you know, or you can estimate that on average each one of us eat approximately 1.5 kilograms of food every day. So it's rightly so that we are very concerned about the quality of the food, whether it's organic, etc., because we eat so much of it. Actually, if we think about the water that we drink, it's a bit more, about 2 liters or 2 kilograms per day. So the quality of water is extremely important as well. And maybe when I do that with a classroom, I ask people to guess, but I will cut the corner short. In fact, on a daily basis, we process through breathing about 14 kilograms of air. So it means really that tiny amounts of pollutants in air matters a lot for our health. Actually, when we say air pollution, it's a mixture of lots of different pollutants, and not all the pollutants affect our health in the same way. What I would like to say is that air pollution is all year round. So there is pollution in winter, in spring, in summer, and in autumn. But these involve different pollutants. And basically, there are 2 types of pollutants. The one we call primary pollutants, so that the one that are directly emitted by human activities, car traffic, industry, etc. So we speak particularly of fine particulate matter. You will see in my presentation PM10 or PM2.5. So that's the fine particles that are smaller in diameter than 2.5 microns, PM2.5, or 10 microns, PM10, so slightly larger particles. Nitrogen dioxide, NO2, and sulfur dioxide, to pick one, also SO2. So these are pollutants that are mostly directly emitted, and then when they are in high concentration near the ground, can cause health effects. But there are other pollutants that actually are formed in the atmosphere. We call them secondary pollutants. And a key one is, for instance, ozone. Ozone is a summer pollutant, or a spring and summer pollutant. You need sunlight and photochemistry to create this pollutant from precursor pollutants. And also some aspect of particulate matter are also secondary. So it's a complex business, and it's not because you know something about pollution by PM2.5 that you know necessarily something about the pollution by ozone. So it means that monitoring and forecasting of air pollution needs to be for a range of different pollutants that affect our health in different ways. So how the situation has evolved, focusing on Europe in the last 15 years. Actually, in terms of air quality, the situation has slightly improved. There have been, at the level of the European Union, a number of laws and directives that for which EU member states commit to reduce their emissions. And year on year, we've seen a slight decrease of the key pollutants. You see PM10, PM2.5 with a fairly clear trend also for NO2. But you see for ozone that the trend is not that clear, and that basically levels of ozone have more or less stayed the same in spite of the measures that have been taken over the years. In fact, this situation is coming from a state which was really bad. So if we talk about the 60s, 70s, air pollution was much worse. And thanks to a number of policies, this has improved, but now it's not decreasing as much as we would like, and we see only this very slow decreasing trend. And what matters is that the level of air pollution in Europe, so I'm not speaking of India or China or other parts of the world that are heavily polluted, we see, and this is from a report of the European Environment Agency, that the distribution of observation of fine particulate matter, PM10 and PM2.5, or of NO2, even if most of the distribution is below the EU limit value, which is this red line, you still have values in excess. So it means that there are occasions where this EU limit value is exceeded. And worse than that, for particulate matter, for instance, the WHO has indicated guidelines of the levels that are safe for health, and that's a black line. They are more stringent than the red ones. And what you see using these WHO guidelines is that actually the situation is not as good as we could think, and lots of occurrences, particularly for fine particulate matter, PM10 and PM2.5, is actually above the value that is currently thought to be safe. So the result is, according to the EEA, in 2018, there was a bit more than 450,000 premature deaths in Europe, mostly due to fine particulate matter, PM2.5, but also to other pollutants like NO2 and ozone. And over the last decade, things have improved, but not dramatically, in line with the decrease in the concentration. So air pollution is a big problem in Europe still, and if we look worldwide, it's even worse. The WHO has estimated that air pollution kills today more people than smoking, with this quite shocking figure, which is there. So the question is, what can we do about this situation? The first thing, and treating the problem at the core, is to decide and enforce policies that are more aggressive or more deliberate to reduce pollutants. And actually, if it is done in an appropriate way, it can also be good for carbon emissions and also for climate. But care has to be taken for that to win both on the air quality and on the climate carbon emission side. So that's the core of it. Now, all these measures, they are difficult. They take money, they take persuasion by policymakers. So what we can do in a shorter time scale is two ways. The first one is to inform a decision maker to launch warnings when there are episodes of air pollution that are particularly bad. So with that, they can inform the population, but they also can take some measures when it is particularly relevant. When a storm is coming in terms of weather, there's no way you can stop the storm. So all you have to do is to brace and pray that you are safe after the storm. But for air pollution, if there is certain meteorological conditions that are very bad for air pollution, maybe if you take measures to reduce car traffic, to reduce emissions by industry or by agriculture, then you can reduce the extent of the episode, and so have a direct effect in mitigating this problem in the short term. But also, everybody can actually benefit from information about air pollution, either as it occurs or as it is forecast to occur, because people can reduce their exposure. So if you have a baby, for instance, maybe it's not wise to go out in the park on a day where there is a high pollution episode, or it's not wise actually to do your sport on that day. It's better not to do your sport for once. But also it helps changing on patterns. So maybe there is a pollution episode, and in order not to bring your own car pollution to the mix, you choose to cycle or to take public transport. And what's very important, and what the program Copernicus is very key contribution to, is that all these decisions and this warning have to be made based on facts, on evidence. It means that this needs to be based on observations and latest science. So you will probably say, after what all we've seen in the news, but yeah, we have satellites for that. And it's true. I took this snapshot from our Copernicus Sentinel-5P instrument, which was taken yesterday. So you can see some plumes of pollutants. Here it's NO2, so one of these pollutants. You see that in several places in northwestern Europe, or North Europe, East also, some plumes of NO2. So yes, this is a fairly new situation. It has been only a few years since we have satellite observations that are relevant for key pollutants. But it's a bit like for weather. If you take this satellite observation in isolation, its usefulness is not so much. The reason is that there are clouds. So yesterday we were lucky. So most of Northern Europe was clear skies, so we could see everywhere. But you can see where it's transparent that there is no data. And in autumn and in winter, it's very often that there is no data at all because there are clouds and the satellite cannot see through the clouds. Also, another limitation of the current generation of satellites is that they come across every point on the Earth, but only once per day. So you have one measurement per day, and as you imagine, pollution varies a lot, just like winds or temperature or precipitation, and so it's fairly limited. So my point is really to say that air pollution is not a mapping exercise. It's something that varies with lots of processes carried by winds, etc. And in order to have accurate information on air pollution, in order to, for instance, to assess health impact, you need to combine satellite observation like these ones, surface observations, because there are a lot of surface observations, especially if we speak about Europe, and numerical models, just like for weather. And that's actually what we do. As an example, in the Copernicus Atmosphere Monitoring Service, we have a global system, which is actually an augmented version of our ECMWF numerical weather prediction system. So forecasting air quality in a way is more complex. You have to add things on top of weather forecast. And you already know that doing weather forecast is something which is very costly, very difficult. Only a handful of organizations in the world deliver very accurate forecast. And for air quality, it's basically the same. So at the core of our activities, there is the concept of data assimilation. So just one slide to explain to you what we do. So we get data. In that case, it's about carbon monoxide, which is one pollutant, which is emitted by all combustion sources, which is very well monitored from space, and different satellite instruments monitor this species. So there is one US instrument, which is called MOPIT, and you can see this swath showing high values of CO in the tropics over Africa and lower value, for instance, in the southern latitude. You see higher value next to Japan and China and Korea. So that's one instrument, but there are other instruments. This one is a European instrument. It's called YASI. It's on board EUMETSAT polar orbiting satellites. And you can see also a similar picture. It's not measuring exactly in the same wavelength, so it's not a one-to-one comparison. And by mixing that with a numerical model, we managed to get a 3D picture of the atmosphere that combines all the information that we can get, in that case, from those two instruments. And from there, we base the forecast. So to give you an example of what we can do, this is not an example about CO, but it's dust, so sarin dust. You can see here with the visible NASA image an outflow of dust that is coming off the way to off from Africa and going all the way to America and going in Puerto Rico. You have small tweets where you can see before and after the strong effect of this very big plume. It was so big in June 2020 that it was called Godzilla plume. And you can see here the capacity that we had to forecast this event up to several days in advance. I skip verification against observation and on the ground, but it was really accurate. So the state of play is very good. And as a matter of fact, and also in the context of COVID, because air pollution is a very important driver in COVID, there have been lots of interest, and I would say increased interest for the question of air quality in the recent 4 or 5 years, with lots of uptake, in particular from our Copernicus information. And air quality actually is becoming mainstream information, when in the past you had only, I would say, weather information. Now it's very common that you can find air quality information. This example in the full screen is from the windy.com platform. So you can see air pollutants forecast together with the values that are actually observed, but also now the weather app on the iPhone, weather channel. There are lots of TV like Euronews or CNN that use air quality forecast and provide daily bulletins, just like it was the case for weather for weather before. So it's becoming mainstream. However, the question comes whether this type of information, and currently the state of the art, as we do in Copernicus, is about 10-kilometer resolution, just like for weather, actually, weather forecast. Is it really useful? And this example, which was done by a Belgian colleague from Vito, is showing simply the effect of averaging information. So they have on top left a numerical simulation of Brussels for one pollutant, NO2, and you can see the city, the streets, etc. And then simply by averaging the pixels, you can see what you see with a 500-meter horizontal resolution, 100, etc., 1 kilometer up to 10 kilometer. And then you see the 10 kilometer sees Brussels only like one of very few pixels of information. So is it really useful? The answer is yes, because information is not only in space, but it's also in time. And for that, I use this example of a site of 2 sites in London. You have in red, it's a time series about for about a month with the values of pollutants. It's fine particulate matter, PM10, which has been observed. So it's observation, no model, surface observation at this site, which is a so-called urban background station. So it's near a park. So it's not directly under the influence of a street. And conversely, the green line is for a sensor which is right in the middle of traffic lanes, so as heavily polluted as you can think of. And what you can see is that, of course, the green line is always above the red line, so there's a kind of constant shift, and there is also more variability. On some days, you see spikes that exist. But overall, the picture that you see with the red curve is basically the main element to the story. So there is an episode which occurred towards the second half of the month. And this is, of course, seen in the course in the station that is a background, for which a coarse resolution is enough. And if you want to know the detail of the peak, the absolute peak, then you have to add on a few the characteristics of the traffic, which is just nearby. So air pollution has to be seen as a combination of spatial information that should be refined at very high resolution, as high as possible, but also time resolution. And for that, from the time dimension, what we provide in particular from CAMS is as good as you can get today. So let me finish now with a few slides to give you some ideas about how, from there, how ideas for the Copernicus call could work. Basically, one of the challenge is about downscaling information, because as I said, information is both in space and time, but for certain applications, you need high resolution, so you need to downscale. There are different ways to do that. A way that was traditionally used, but is very costly, and this is, for instance, what the Finnish Meteorological Institute is doing, is to use a cascade of numerical models. So the models are very detailed models of the atmosphere with lots of information about also emissions, etc. And they can forecast, starting from the coarse resolution that we provide at the scale of Europe. They can focus progressively on the Scandinavian peninsula, and then on the area of Helsinki, and then on the city of Helsinki itself. So that's a method of downscaling. What is good is that you don't need to start from scratch. So in that case of Helsinki, having the information at European level means that if there is plumes from Saharan dust or a plume from wildfire, as we've seen coming from North America, this will be captured and flow into the domain without, if you're interested in Helsinki, you having to do all the work to look at all the sources across the world. But there are other approaches and to downscale air pollution, and artificial intelligence is, I would say, super promising, or even more than promising, because it's already proven as a very good approach to downscale this information, particularly in space. And this is an example from Rochelle Schneider, who was working in the UK, now working at the European Space Agency, was described in this paper how to map fine particulate matter, PM2.5, using a sensor, satellite, and model information. If you use only sensors, you see here the dots that she had for this exercise. You cannot really map the whole of England because there are lots of holes. But by adding satellite-based products and forecasts, you can reconstruct fine particulate matter, as she has shown, using artificial intelligence in a very efficient way. And by doing that, you can do health assessment of better quality. So that's one approach, and this approach could be encouraged and could be replicated in other parts of Europe or of the world. There are other approaches also. People have been looking, and for a long time, at questions at super high resolution. And super high, I mean really the street level. And this is an example from colleagues in Denmark who are forecasting and estimating air pollution on two sides of a big street. And depending on how air is circulating in this street, you can see for a number of pollutants with the dashed black and the blue lines, that actually the concentration are pretty different. So it makes a difference to walk on one or the other side of the street. So downscaling can go as far as that. And if you think coupling that with a mobile phone localization, you can see that exposure could become really assessed in an accurate way. Because in fact, exposure, it's not a matter of maps. Of course, maps and high resolution maps are very useful to have a first go at exposure. But in practice, we have to estimate how we are exposed to air pollution. And in order to do that, so that's something that I started long ago, several decades ago, but which is improving recently. It's about assessing how we spend our time. So here in that case, the person is sleeping or resting for 46%, doing outdoor activity 4%, etc. So you have your budget of time, and then you can estimate in what environment you're doing this activity. So indoor at home, 58%, outdoor, etc. And then it's a matter of assessing what are the concentration of key pollutants in these different environments, and this can change in time. So you can actually make a full budget of the exposure of the person, not only based on the position of the person, but also based on what the person is doing. To take an example, for instance, if the person drives his or her car to an indoor car park, it's actually a super bad environment. Indoor closed car park is as bad as you can in terms of air quality. So even if you spend 5 minutes in this type of environment, it will actually mean something for your daily uptake of pollutants. And for some of the environments, there are predictive models for all that is outdoor, depending whether you walk or you run or you do cycle. It is possible to go towards what we call personalized medicine. So having a really access to what is your personal exposure, and not only a map where you pinpoint the place where you live, but it will depend on how you spend your day. And actually it can be a tool also for you to see how to improve and reduce your exposure to air pollution. My last example before finishing and answering maybe some question is an example that was done by colleagues in Lithuania in the University of Šiauliai. And it was a development of a system which is called PASIFO. It's not about air pollution, it's about pollen. So as you may know, about a quarter of the European population is allergic to pollen. And as CAMS, the Copernicus Atmosphere Monitoring Service, we provide a pollen forecast as we provide a forecast of air quality. But knowing the forecast of the number of grains of pollen in the air is interesting, but not that much. What does it mean for you? So what this application was doing was to enroll a number of people suffering with allergies, and training for a while the system to ask people, how do you feel today? So the person would say something between 1, I'm fully okay, to 10, or very bad symptoms, especially my eyes or my nose, etc. And then by training the system, and artificial intelligence is also an avenue for doing that, it is possible to deliver forecasts that are specific for this person. And on this test case, we could see that the PASIFO system managed to predict quite well, actually, day after day, how the symptoms of the person would evolve. And with allergies, what is very good, it's possible to take medication in advance. So it means that by doing that, if you have a forecast which is personalized, so you know that's something that is really related to you and how you felt in the past, it will tell you, well, you really should take your medication today if you want to avoid the very high symptoms tomorrow. So that's also my word is just to say that now it's up to you. I hope that I've excited a little bit your curiosity about air quality and health, and I'm very happy to answer any question either now or offline. Thank you very much.
Thank you very much for this great presentation. Very, very interesting indeed.